Hello.
Okay, welcome to the second day of our Q lectures. Today, Professor Diaconis is going to tell us about adding a list of numbers.
Good. Okay, thank you. I hope this works. And hello. Thank you. Oh, I didn't do it. But, nice to be back, and nice that you're here. So, in order to try to make the talk self-contained as I can, I want to begin where I left off yesterday, and I had two subjects, adding numbers and shuffling cards, and I was trying to say that they're closely connected. Today's lecture is going to be about adding numbers, and the last lecture will be about shuffling cards, so to try to develop them a little bit. But I remind you that if we add in numbers with base B, then the carries were, well, kappa 0, which was 0, kappa 1, kappa 2, are numbers between 0 less than or equal to kappa I less than or equal to n minus 1. And so, for example, if I add 3, 2, 9, 7, 5 to 2, 5, 6, 1, 4, it doesn't look so good for carries, but anyway, let's do it. This is 9, this is 8, this is 15, and to show this a carry, I put a 1 there. This is 8, and this is 5. So here there's one carry, so kappa 0 is 0. There's never a carry in this column. And then kappa 1 is 0, kappa 2 is 0, kappa 3 is 1, and kappa 4 is 0. So there are the carries when we add numbers as we go along. And then if we riffle shuffle in cards via B shuffle, and I explained what that was. You cut a deck of cards into, say, B is 3, into 3 piles by a trinomial distribution, and you start dropping the cards with your 3 hands, each time dropping a card from a pile with probability proportional to its packet size. That's what I meant by B shuffles. So P sub B of permutation sigma, there was this nice formula. So it's a probability distribution on the symmetric group. It's n plus B minus R, choose n divided by B to the n. That followed from in an easy way, where R, which is R of sigma, is equal to the number of rising sequences, and it's also equal to 1 plus the number of descents in sigma inverse, where the descents are the up and down pattern in a permutation. And so there was a formula for this, and you could repeatedly, you could B shuffle once and B shuffle twice, and keep going, and so let D0, which is 0, D1 is equal to the number of descents in sigma 1, the number of descents in sigma I don't know, K, be the number of descents when, okay, so start the deck in the identity, shuffle once, you have some pattern, shuffle again, you have a different pattern. Each time you record the how many descents there are. And then I asserted that the probability that kappa 1 is epsilon 1, kappa 2 is epsilon 2, kappa m is epsilon m, say, the chance of having, carry of epsilon 1 in the first column, carry of epsilon 2 in the second column, etc., was equal to the probability to be shuffling that the number of descents is equal to epsilon 1, number of descents after the second shuffle is epsilon 2, the number of descents after the nth shuffle is epsilon m. And this is true. This is true for all deck sizes n, bases b. What other parameters are there? However far I want to go, m, epsilon 1 up to epsilon m. And so the two processes are exactly the same. Now, let me stop here for a second. If anybody wants to ask a question to clarify or to give me a hard time or to remind themselves about definitions, does anybody have a question? It's okay. Or is everybody was here and it's crystal clear? I haven't said anything yet. Okay, so that was where I ended last day, trying to make a connection between adding numbers and shuffling cards, and if that's not a connection, I don't know what is. Okay, so the next, the start of this lecture is to try to answer the question, why is this true? Why? How do you prove it? What's going on? So let me start there. Now, as I said last day, this is a serious world-class math environment. And you might have thought, this guy is going to talk about adding numbers, shuffling cards. How low can you go? I'm going to talk about adding a single column of digits. Don't throw things. So here they come, 7, 5, 3, 8, 4, 4, 6, 9, I don't know, 5, I don't know. So let me try first to get it right, and you can help me. This is 14, 24, 28, 36, 39, 44, 51. But I think it is off by 1. It should have been 52. But anyway, I'm gonna do that again slower, and you can check with me. So I'm gonna do it from the top down. Here's 7. I just copy 7. Now 5 and 7 are 12. So there's 12. There's the 2. And to show that I had a carry, I put a dot. Okay. 3 and 2 are 5. Nothing. 8 and 5 are 13, and to show that I had a carry, I put a dot. 4 and 3 are 7, 4 and 7 are 11, and I had a carry. 6 and 1 are 7, 9, there's no carry, 6 and 1 are 7, 9 and 7 are 16, and there's a dot, and 5 and 6 are 11, and there's there's a carry, and so there are 1, 2, 3, 4, 5, 51 is the sum of these numbers. Okay, so if you haven't seen it before, this idea of using dots is familiar to bookkeepers. It's a popular system. It's called the Trachtenberg system. Trachtenberg system. Speed arithmetic, but bookkeepers use it. If you type it in, it has its own Wikipedia entry and its own literature. And okay, if you're me, and now you, because we've been in this for an hour already, it's natural to ask, how do the dots go? So question, how do the dots go? That is, how many dots are typical? You know, how many carries are there when you add a column of numbers? And if you just had a dot, is there more or less likely that there's a dot after it, that there's another? That kind of question, you're following it. And so that's a embarrassingly simple question. And let me make two claims about this. So throughout, in answer to a question at the end of last day, but throughout, every time I'm picking digits, I'm picking them independently. Here, my digits are uniform on the uniform distribution on 0, 1, up to b minus 1. So I'm picking my digits at random and independent of one another. So typical numbers, how many carries are there? And you could try to change those rules, but this is now almost a well-defined math problem, or setup. And so I make two claims. The first is, what are my two claims? If left-hand digits are IID, that just means independently, uniformly distributed, you know, according to this rule. If the left-hand digits are picked at random, then the right-hand digits are IID uniform. So, of course, you might think, gee, don't they get all tangled up? But this is very easy to see. If, first of all, certainly 7 is a random digit because I just copy it. So that's a uniform random digit to start. And if I add, picture the 0 up to 9 here, picture the integers mod b. If I add a random digit to 7, it's random and independent of 7. Right? That's equally likely to be anything. It doesn't depend on what I added it to, right? So that's an easy claim, right? And it just keeps going. Right? So that's the first claim. And the second claim is that there's a carry on the left-hand side, if and only if there's a descent. On the right-hand side. And so you can first see that that's true. You know, here 7 goes to 2, 5 goes to 3, 7 goes to 1, 7 goes to 6, 6 goes to 1. And that's baby arithmetic, so you can figure that out. It's adding two numbers, right? So that's not so hard to see. And so there's a close connection from these two easy claims between carries and descents in a sequence. And whatever else I say, and I'm going to say a lot of other things, the analysis of the dot process, the carries process, is equivalent to a basic problem in classical probability. Take a sequence of random digits and look at the up-down pattern. You know, what proportion of times do they descend or not? And this version of it, the discrete version, actually has had almost no development. Everybody assumes that you take random points uniformly between 0 and 1 continuously. And here there are ties, and then it's harder, a little bit more complicated. But so the understanding the dots from the point of view of the right-hand side solves problems that go back to Laplace. And okay, so that's my talking. It's starting to talk about adding a single column of digits. And a key remark is the following. This explains star, this is star here. That is, star says there's a connection between carries and descents, riffle shuffles, descents. And you can prove this theorem by these kinds of elementary these bijective arguments. And it's too complicated for me to do in public. It's not, if we had an hour or something, and I have a lot of things I want to tell you, but how you expand this observation is, first of all, instead of single digits, you have, you replace this by columns of digits, and then you have to make a notion of carries for each row of a column of digits, but that's an obvious thing to do. And of course, the right-hand side gets replaced by columns of digits. And then if from the right-hand side, you associate columns of digits permutations, and it's a straightforward thing to do. And the descents in doing that are the descents in the permutations, and you can bijectively see this theorem. So that's the second proof that I found of this. The first proof was pretty hard, symmetric function theory, and if you wanted to see it, well, you should see it at your leisure. And in the handout, there's a paper that I wrote with Jason Fullman in the monthly, in which we shuffling cards and adding numbers. Maybe that's what it was called. I don't know. But and we spell it all out. The monthly is a very readable undergraduate type journal. And so if you wanted to, if you understand this, you can understand the proof of this theorem. But then you'd have to want to understand the proof of this theorem. It's some honest effort. But it's an elementary aha argument. After first observing that this was true, as I talked about yesterday, and then finding a hard analytic proof, and then finally we found this dot proof. And so I'm not gonna try to say more about that now. What I am gonna do next is to tell you about how strong I am. Some properties of carries. Okay, so and there are two reasons to tell you about that. First of all, people really do add numbers, and they make up numbers. And I don't know, but if you look at the Wall Street Journal maybe 2 or 3 days ago, bookkeepers have found that the distribution of digits and numbers that people make up are off. And you can tell on both tax returns and financial documents whether they're real numbers or somebody fooling around, if you want to phrase it that way. And so these are, people are interested in adding numbers. It's a pretty basic thing. But the second half of this talk is all about something that's called determinantal point processes. And there are thousands of examples from particle physics and random matrix theory and graph theory, and all of the properties that I tell you now about digits apply to all of those examples too, so it's not a bad thing to touch them in the simplest case. So, so some properties of carries, or equivalently descents. So I'm going to let xi be equal to 1 or 0 as there's a dot in position I. 1 less than or equal to I less than or equal to n minus 1. And you know what I mean. I'm adding n numbers or writing down a sequence of n numbers. And this is the first position, second position, third. So here, x1 is 1, x2 is 0, x3 is 1, x4 is 0, x5 is 1. So just going to let xi be whether there's a dot or not. And the first question is, so there's a bunch of facts. So fact 1 is the probability that xi is 1, the chance that you have a carry, and doesn't depend on where we are, is b choose 2 over b squared, which is 1/2 minus 1 over 2b. So the chance of having a carry is a little less than a half, and let me prove that once and for all to prove something on the two sides of the argument. So proof 1. So let's make a kind of children's carries matrix in which 0, 1, 2, I'll do it, b is 10, but I'll do it up to 9, 0, 1, 2, up to 9. So those are the possible places. What is this question asking? Pick 2 digits at random. What's the chance that when you add them, you have a carry? So let's just do it by brute force. If I add 0 to anything, I don't get anything. 0, 0. If I add 1, I only get a carry if I add it to 9. If I add 2, I get a carry if I add it to 9 or 8. So this is a 1 here, and then it's a 1 here. ... If I add 9, I get a carry if I add it to anything except adding it to 0. So just by inspection, that's the number of carry. I mean, that's how the carries go. And this is 1 plus 2, up to b minus 1. So the number of ones in this array is the number of ones is b choose 2. That's the b rows, and the first row is all 0, and then pick 2 digits at random. The chance of picking each digit is 1 over b. So that's why that's a description. That's proof of that just by looking. And similarly, if you look on the right-hand side of this picture, and you know this fact too, pick 2 digits at random. What's the chance that the second one is less than the first? Well, you have to pick 2 different digits. The number of ways of doing that is b choose 2, and then pick 2 digits at random. So it's very often easier to argue on the right-hand side than on the left-hand side. But so these that's the start. The second fact is that the chance of having j carries in a row, chance that let's say xi is equal to 1 xi plus 1 is equal to 1 xi. You get I wrote it down because it's easy to write it down wrong. So where's fact 2 and the I plus j minus 1? Okay, that's so I plus j minus 1. So this is the chance of having j carries in a row, and this same argument shows you that is b choose j plus 1 over b to the j plus 1. So that's just either of these arguments will do that for you. And so in particular, you can't have more than b carries in a row. Right? This would be 0 if j is b or more. That's maybe not obvious at first sight, but also, so corollary, the covariance, the covariance of xi and xi plus 1, which is equal to look at the chance that xi and xi plus 1 is 1 minus the expected value of xi times the expected value of xi plus 1. So that's the correlation between two consecutive digits. Well, this is the chance of having two ones in a row, and this is this number, and so we know what it is. And when the dust settles, it's minus a 12th times 1 minus 1 over b squared, and 12th. And so the consecutive digits aren't independent, whether it's consecutive, whether there's a carry or not, or whether there's a descent or not, aren't independent. They're slightly negatively correlated, and that's what the correlation is. So as b goes to infinity, it goes to minus a 12th. And okay, so that's good. Fact 3, which is stationary one dependence. So the carries process is it's a random process. I mean, x1 up to xn minus 1, they're random quantities, and they're stationary, meaning that if J is a subset of n minus 1, any set of positions, such that such that shifted J plus I is also contained in n minus 1. So, look at the positions 1, 3, and 5, suppose n is 100, and then shift over by 20. Okay, so 21, 23, 25, that's a typical thing. Then the chance that the chance that xj is equal to epsilon j for j contained in j is equal to the chance, I'll explain this, xj is equal to epsilon j for j contained in the set shifted over by I. So, look at 3 or 5 positions. What's the chance of a given pattern? It carries there. It doesn't depend where you are. That is, you can shift over. It's just, that's what stationarity means. And that's just obvious if you think about it, but it's important. This is stationarity. So this is stationarity. And then one dependence is if J is a set of possible positions, and with the property that for that J and J prime are in J, then they're separated by at least 1. J minus J prime is greater than or equal to, is greater than 1. Greater than 1. So, maybe J is 1, 3, 17, right? It's a set where there are no two consecutive elements. Then the probability that xi is equal to anything, epsilon I for I contained in J, the joint distribution of carries is equal to the product of the probabilities that xi is equal to epsilon I for I contained in J. So that's what one dependent means. If you look at digits that are separated a little bit, then they're completely independent of each other. And that's something easy to see from the descent point of view. It's a little more complicated if you think on the left-hand side, but if I have two digits, that are separated, whether this is smaller than or bigger than this doesn't tell you anything about whether this is smaller than or bigger than this. 7 doesn't have anything to do with what's above it. It's easy. These are elementary facts, but they're important. So as a corollary of these, if you look at how many carries are typical, if you add n numbers, a column of n numbers, let Tn be x1 plus x2 plus xn minus 1, that is the total number of carries, the number of dots in the column, then the average value of Tn is equal to, well, there are n minus 1 copies, and then this is times a half minus 1 over 2b. The mean of a sum is the sum of the means, no matter what you want to say, and the variance, of, let's call it sigma squared of Tn, how it wiggles about its mean, and let me get the constants right. It's n plus 1 over 12 times 1 minus 1 over b squared. So the mean and variance we know, and then the central limit theorem holds. The bell-shaped curve is here. Did I write an error term on it anyway? The probability that Tn minus its mean divided by its standard deviation is less than or equal to x is, well, let me write it down, minus capital Phi of x, the area of the bell-shaped curve, is less than or equal to 0.8. This is true, divided by the square root of n. But so how many carries are there? Well, there are around, this number times the length of your column, so around n over 2, a little less. And if you subtract off the mean and ask what's the chance that it's within 3 standard deviations of the mean, it's given by the area under the bell-shaped curve to the left of x. And this follows because there's a classical central limit theorem for one-dependent processes, and so it's just free if you can compute the mean and variance, and we have. So we're beginning to get some feeling for how the carries go, and okay, the next one is important a little bit, and so because of physicists use this language, so fact 4, if that's where I am, which is k-point correlations. That's what it's called, k-point correlations. And let A be a subset of 1 up to n minus 1, a set of positions size k. So, okay, and you can ask the chance, if you pick a random sequence, instead of just the ordinary correlation between 2 places, k-point correlations are, so look at the chance that xi is equal to 1 for I contained in A, okay? That's usually called rho of A, and it's called a k-point correlation, okay? That's just, I just defined it. So what's the chance that there's a carry in positions 1, 3, and 17, and maybe other places, but I'm not asking about that. I'm just asking about what's the chance that there's a carry in those places. And this is nice. The fact is, well, maybe it's nice. Let's write it so you can see it. Remember, you're going to see these objects again, but well, so rho of A is equal to, it's pretty nice. It's the product from I equals 1 to m of B, get it right, AI plus 1 over B to the AI. So whatever it is, that's a nice formula where A is equal to A1 union A2 union AM, where AI are consecutive. So you can express your positions as a disjoint union of a bunch of consecutive blocks. It's maybe easiest to do an example. If A was equal to 2, 3, 5, 6, 7, and 11, then that's equal to 2 and 3, 5, 6, and 7, and 11. So you can express your sequence as a disjoint union of consecutive blocks, and the length, this is A1, A2, A3, and the number of blocks is M. So if you want to know what's the chance that you have a carry at these positions, what you have to do is ask your positions to speak for themselves, and then there's this nice formula. So there's a nice formula for the k-point correlations. And the final fact that is maybe the key to the rest of this lecture, and an important thing, is fact 5, which is it's a determinantal formula. I should say, I mean, this fact follows from facts 3 and 4. I mean, it's just right. The determinantal formula looks a little messy, but you get used to it. So let epsilon 1, epsilon 2, epsilon n minus 1, I'm talking about n minus quantities, be fixed in 0, 1. So just the possible carries. Then the exact distribution, x1 is equal to epsilon 1, xn minus 1 is equal to epsilon n minus 1, is equal to, well, 1 over b to the n times the determinant you have to get used to looking at, and I'm still sj plus 1 minus si plus b minus 1, choose b minus 1. So let me explain this determinant, where there are ones in epsilon 1 up to epsilon n minus 1 in positions S1 less than S2 less than Sn minus 1. So look at the question you're asking, look at these epsilons. There are some ones, maybe there are 2 ones, and all the rest are zeros. And maybe the first one is in the second position, the third one is in the 15th position. So those positions are called SI, and those are these SIs. And because I'm going around the corner, S0 is 0 and Sn is n. And so there's a closed form formula, determinantal formula, for the joint distribution of the number of carries. And that's not so easy to prove. It wasn't even, I felt brave for guessing at it, but anyway, it's true. And I'm not going to do an example, but we will do some examples of similar formulas. I had one written down, but I don't want to get lost in that. So these facts, and let's just say where we are, I'm talking about a very simple example, adding a list of numbers, or look at the up-down pattern in a sequence of numbers, and then we kind of know how it goes, right? We really, these things let you answer, what's the chance that there's a whole of that there are j places that are 0, or any reasonable question, what's the length of the longest sequence of ones? Any reasonable question, once you have these formulas, you can answer them, and you have a feeling for how the carries go. So there's a huge class of processes for which exactly the same kind of formulas hold, and which includes carries as a special case. And so that's my next topic. So whether you like these specific examples or not, so here comes the second main topic, and this is an important part of modern probability, modern mathematical physics, and modern a lot of other things. And the subject is called determinantal point processes. Determinantal point processes. Processes. Okay, so that's a subject, and the handout has lots of references, and I'll try to explain a little bit why I told you about the ones I told you about. And okay, so first of all, I'm going to do it in a finite setting, but it works in very general spaces, Polish spaces. Let X be a finite set. It might be the integers from 1 up to n minus 1, but it could be, lattice points in a grid. It could be any kind of thing. Let X be a finite set, and we define so first of all, a point process. Point process is a probability on all subsets on 2 to the x. And how you should think about it is, so you've got your space, and there are some random points on it. And what's the chance that there's a point here, here, and here, and no points anyplace else? That's a subset. Here, here, and here are a subset, and I'm assigning a weight to each subset. So you look confused. Am I confusing you? It's because if you're confused, everybody's confused, or many people are confused. Can I help? That is, maybe it's on a grid, and I say, I look at all subsets of it's an n by n grid. I look at all subsets of the n by n grid. For example, the middle coordinate, that's a single point, or the middle coordinate in this corner, that's a subset. And I have to assign a probability that the random process has a dot at points in that subset and not otherwise. And so you can imagine, for example, if it was a field where the trees grow, that's a point process. And that process, that's a point process where the dots are. Right. So for every subset, I can say, so a point process just is a probability. So that, you have to, it's a lot of numbers. So for all subsets, you have the chance of that subset. And if you sum it up over all possible subsets, you get 1. That's what it means to say you have a probability. That's a point process. It's a random, where the students congregate. Lots and lots of point processes in the world. So a point process is a probability on all subsets of a given underlying space, and it's P of A for any subset, like the midpoint and the right-hand corner. There's assigned a number P of A, which depends on A, of course. Right? Sure. Right. P is, you have to say what P is. I mean, so this is math, and so for every subset of my X, I've assigned a number P of A. I have a recipe for assigning a number P of A, which is non-negative, and such that if you sum it up over all 2 to the absolute of X subsets, you get 1. So does that help? You could. I don't know that that's not where we're going, right? So, that's a determinantal point process, as it turns out. I mean, but or you know, if you look at a field and see where the trees grow, or that you know, when you make a grid and you put a 1 there, and then something, so it's a random point process. It's a measure on points in a space. Okay, well, examples coming in, maybe that'll help, and if not, you're helping everybody to slow me down. So a point process is determinantal. Point process is determinantal. If there is a kernel, there exists a k of xy for xy contained in x. So there's some non-negative function k of xy for xy contained in x, such that the chance, such that the probability such that rho of A, the chance that the random set that occurs when you pick the points at random contains A and maybe some other things is equal to the determinant of k of xy, where x and y are contained in A. Here, just so rho of A. So if x of x, so a point process is a way of picking a set at random. I've given you, for each possible set, I've given you a weight, and then you can imagine picking a random set A with those weights. And if I let, for each point in x, x of x is equal to 1 if x is in this random set and 0 otherwise, that's the indicator function, is there a point or not? When you've picked this A, rho of A, this is equal to the probability that x of x is 1 for x contained in A, so that you have points at all the points in A, there's a dot at all the points in A, and then you're not specifying anything otherwise. So that determines the measure. And what you could see is that it's somehow easier to define a kernel. You know, that's just you know, something defined for pairs of numbers than to find a measure on all possible subsets of a given space A. And the point of the next, half hour or so is going to be that there are lots and lots of point processes that occur in lots and lots of both applications and theoretical mathematics, which are determinantal. And then it'll turn out that all of these kinds of facts also occur. And so you have a pretty good idea of how they go. And just because I'm going to do it in my examples, if x is a general space, measurable subset of a Polish space, something like that. If x is general, you still, it's just exactly the same definition. You have to do the math a little more carefully. The probability that x of x is contained in xi for less than equal to I, less than equal to n, is equal to the determinant of k of xi, xj, xj are contained in A. So, that is, suppose, as it's going to be in a second, suppose that my space is the unit disk. And I have some way of making random dots in the unit disk. And then you could say, well, what's the chance that there's a dot, here, here, and here, and no dot over there? So that would be a point process. And the point process is determinantal if it's k-point correlations are given by the determinant of a kernel. So well, examples I hope will help, and if not, we'll go back and I hope everybody's reasonably comfortable with the finite case. So before going on, let me tell you some examples. So examples, determinantal point processes were first studied by physicists, and there's a wonderful lady named Machi. And she was studying, so in quantum mechanics, where fermions appear. In quantum mechanics, that's random, and so you can where the energies, what they are, and she noticed that for a lot of the models that are standard in quantum mechanics, that the probability distribution specified by quantum mechanics for fermions was determinantal. And she's a good mathematician, and so she abstracted it and essentially gave these definitions. And she's still with us and quite a hero of mine. So that's the first place they appeared in this way. The eigenvalues of random matrices random matrices so let me be specific. Let UN be the usual unitary group. The set of all matrices such that NM star is the identity. So n by n complex matrices with this property, and the eigenvalues of M contained in UN are points in the unit circle, because unitary matrices don't stretch or shrink, they preserve length. And so pick a matrix at random. By that I mean Haar measure on this compact group. So pick M contained in UN from Haar measure. I can explain what that is better, but not unless you want me to, from Haar measure. It's not hard to explain, Haar measure, but just pick a random matrix. And so it has n eigenvalues, and the eigenvalues form a determinantal point process. The eigenvalues form a determinantal point process on S1 with kernel k of, say, theta prime. It's the sine kernel. It's equal to sine pi theta minus theta prime over theta minus theta prime. So that's pick a matrix at random where the eigenvalues. There's a lot of interest in that from various points of view. Number theory in particular, the eigenvalues. If the n is large, the eigenvalues look like the zeros of the Riemann zeta function, we believe, and it seems to be true. And there's a very, very careful, exact. So it's it's exactly a determinantal point process with that as its kernel, right? So not approximately, not asymptotically. It's a determinantal point. So any question you want to know, you can get your hands on by massaging the sine kernel. Here's a finite example. Fix a, say, connected graph. Fix G a finite graph, usual graph, undirected simple graph, finite graph. Pick T, random spanning tree. So I hope so I have a graph, and then the spanning tree is a connected subgraph with no cycles. So pick, and there are finitely many of them because the graph is finite. So pick a spanning tree at random and let xe for equal 1 if e is in t and 0 otherwise. So look at the process defined by the edges of what edges are in the spanning tree. So pick a spanning tree at random and then look at what edges are in it. That's determinantal. Random analytic functions. So this is a huge set of examples, and I'm only going to say one, but I'm trying to make the point that there are a lot of things that are determinantal in many, many different walks of life. So let f of z be equal to the sum from j equals 0 to infinity of xj z to the j, where xj are independent, identically distributed random coefficients from the normal distribution, the bell-shaped curve. So make a random power series, and of course this will only converge if z is less than 1. Here z is less than 1, otherwise it needn't converge, but it certainly converges on the unit disk. And you can look at the zeros of a random power series, right? So pick a power series at random. What do its zeros look like? We pick varieties at random too, if that makes you happy or what. You're behaving yourself, and so am I. Okay. But then the zeros of f of z, those are random points because the power series is random, are determinantal with kernel. The Bergman kernel, so you have to learn some complex variables, but k of zw is here, it's 1 over 1 minus zw bar squared. That's here, z and w are contained in the unit disk. So, and you can, there are hundreds of similar things. Well, I'm not gonna. Let me do the Geneva ensemble. Geneva ensemble. So pick M contained in mat N with I, D, normal, complex coordinates. So take an n by n matrix, empty one, and then fill it up with picks from the bell-shaped curve. Okay, that's a matrix. And look at its eigenvalues. There'll be complex points in the complex plane. And because the matrix is random, the eigenvalues are random. And what do they look like? Well, they have a beautiful distribution theory, and kernel is k of zw is equal to e to the z squared plus w squared minus zw bar. So I'm going to stop because I've given out references to hundreds of other examples. If you're interested in this, let me, for a second before proceeding, look, if you have access to your handout, let me say a few things and then I'll come back, finish my talk or continue my talk. So if you wanted to learn more about determinantal point processes, so pick a partition of n, either uniformly or from the Poincare measure or from some other measure, write it in Russian notation. What does that mean? So the usual way of writing of doing a partition is this way. Right, that's one way of writing a partition, right? Yeah, okay, and if you tilt it 135 degrees, so it looks like that, just tilt the partition 135 degrees, and then where the valleys are, put a dot. So if I pick the partition at random, say uniformly or from the Plancherel measure or from Schur measures or McDonald measures, if I pick a partition from some measure, the dots are random because the partition are random. And for many, many measures, in particular, uniform, Plancherel, Schur, and McDonald measures, this is a determinantal point process with a nice kernel. And so all kinds of theorems about the shape of random partitions follow from the fact that it's determinantal and so forth. So I'm sorry, I'm going to stop giving examples because they have to be all of this. Each of these could be a talk, and I'm not doing that talk, but I hope you get a feeling, gee, there are a lot of determinantal point processes. Maybe it's something I should learn what it is, you know, because most people don't know. Most mathematicians don't know, most probabilists don't know. People you should know. They're all over the place, and they're useful, and they're being used. So in this, so if you wanted to learn about determinantal point processes, Alexei Borodin's survey is short and it's math, and it's very, very good. Well, it turns out that carries form a determinantal point process. I'm coming to that, and I'll give you another 25 examples. So, but if my writing about determinantal point processes is in paper with Jason Fullman, and let's see. Here's an important one. In machine learning, recommender systems, that is, what should, you know, I don't know, Facebook recommend to you? It's going to recommend a list of movies or a list of products or that kind of thing. And determinantal point processes have negative correlations. That is, the points spread apart. And what that means is that the lists that they gave you will contain different things which are distinct. And so people are using determinantal point processes as with carefully chosen kernels, which reflect the data and the user. And there's a question of, given past behavior, how do you estimate K to approximate well by a determinantal point process? People are using a determinantal point process and determinantal point processes, and then Markov processes on determinantal point processes as basic units in recommender systems. And if you wanted to learn more about that, looking at this nice article by Emily Fox and her two co-authors, Markov determinantal point processes, is a good place to see. A marvelous expository article about random analytic functions with full proofs is in this little book by Huff, Krishnapur, Perez, and Valenvirag, Zeros of Gaussian Analytic Functions. It's short and very good. And one more reference, everybody here knows that Jenny He won the Fields Medal last time, and Jenny has made matroids respectable. And so there's a marvelous connection between determinantal point processes and matroids, and Russ Lyons wrote very, very nice lists of 100 examples, and again, of determinantal point processes. And the basic good article, which has all the details and does it in general spaces, is this article by Soshnikov, but you'd have to want to really read it. It's a good article, it's long, and it's detailed, and so that's a good place to read. So I'm trying to tell you that there's a subject called determinantal point processes, I think. And if you want to look, there's a lot of people who want to tell you what it is. So it's very nice math, and then you have to learn how to manipulate them, well, so I just gave you some examples of determinantal point processes. What are some properties? Well, the analogs of those things I told you about before, they're all kind of true. I mean, some little bells and whistles, but basically you could take any positive definite kernel and make a determinantal point process out of it. I did make an example. So there's another subject which I'm not going to talk about, which are called permanental point processes. There's something called a permanent, an important ingredient in various parts of mathematics, and it's like the determinant without signs, and there's exactly an analog of permanental point processes. The difference is you can compute determinants and you can't compute, computing the permanent is sharp P complete, but meanwhile as math, you can write down things, and so there's an analog of permanental point processes, and I gave you an example in the handout at the top. So the Poisson point process is just random, like raindrops at random. So the chance, just completely random points, and that's a realization of a point process. Realization of a determinantal point process is here, and you can see the points are kind of staying apart from each other, and they're still random. And then this is a permanental point process, in which permanent replaces, I said what the kernel is, but just take the permanent of the matrix. But that has clumping, and the points kind of clumped together. And you could imagine a biologist or somebody who was studying where the trees grow, or where does spatial patterns in housing among minorities, what parts of a city are inhabited by minorities. That's a random process, and you could try to make mathematical models, and these kinds of processes are fit all the time in spatial statistics. Okay. So there are analogs of facts 1 to 5, and I'm just going to say 1 or 2 of them. Properties. The first is that specifying a kernel is easy, relatively. And assigning a measure to 2 to the x, is more complicated. As measure on the space of all subsets, now pretty soon you're talking about a hardish problem. And kernel, it's easy to write down k of xy, many k's of k of xy's. It's positive definite. You can say something about the eigenvalues, and then use the spectral decomposition of a matrix in order to do that. And but this is a convenient way to specify huge classes of point processes, and so that's one thing that they're good for. The expected value, the chance that there's a point is k of xx. So the kernel tells you how likely that there's a point. The covariance of x and y, the correlation x and y is equal to, I see, I misjudged the time. So I'm sorry about that. Somebody should have yelled at me. Maybe that's what. Okay, you were about to yell at me. Okay, so many things are easy if you have a description of the kernel, and if kernels converge to a limiting kernel, then the point processes converge, and that's the basis of all kinds of beautiful math. Okay, what I would have told you in the last minus 10 minutes, really sorry about that, is that carries are determinantal point processes. The descent set of a random permutation is a determinantal point process. The peaks in a random permutation are a determinantal point process. And hundreds and hundreds of determinantal point processes occur naturally in combinatorics. I'm around for the next week, so let me just say this sentence. If you want to ask me, come to my office. There's a beautiful connection between determinantal point processes and Cazul algebras. And so if you know what a Cazul algebra is, come and ask, and I'll be happy to describe it. So what I wanted to do in this lecture is two things. I wanted to explain to you why it's reasonable that there was a connection between carries and descents, and I think that picture does explain it. And then if you want to know in more detail, I told you where to look. And then I wanted to give you an introduction to determinantal point processes. I'm sorry for going over. Thank you for your patience.
So in the interest of time, are there any short questions?
Hi. I hear you.
Stupid process, first one. Do we have some kind of central limit theorem as a limit?
Or are they limiting? Well, first of all, if you call fermion stupid, I'm afraid something's stupid, but it's not the processes, it's you. So I don't want to engage in that kind of debate. Sure, that's what I said at the end. That is, there's a limiting theory, and determinantal point processes have central limit theorems. That is, if you look at a set, pick a configuration, and look at a set and look at how many points there are in a set, that obeys the central limit theorem, for example. Sorry you feel that way. It's a pretty hostile question.
So maybe the last question.
Just one question. Based on the definition that we got about like the point processes, like, is there any restriction about the elements of the set to be different, or they could be like the same? Like, I mean, like, for example, because this one looks exactly like, for example, selecting from a set, right?
It's not for multi-sets. You have to specify an underlying set, like 1 up to n, or all permutations, or the unit disk. I don't know about determinantal point processes for multi-sets, if that's what you're asking.
Basically, yeah, kind of. Like, I mean, like,
you could make marked point processes. That is, you could make points, and then what's on them, instead of being 0 or 1, is an element of some other set, right? Okay. That is, and there are determinantal analogs of what are called marked point processes, but oh, come on, a subject that has hundreds of examples, give me a break. I mean, that's enough. It's enough examples. But there is more to do, and if you have a problem where that's a natural thing, starting there and trying to think, well, how would I do what I want to do, is, of course, a great way to start to do research. Right?
Okay, let's thank the Diaconis again.